Hi, everyone, and welcome back. Today, we're going to be talking about something no one talks about, AI. Obviously, very niche field. No, but seriously, we're going to be talking about the origin story of AI. There's some truth in AI being a niche field, by the way. So, 10 years ago, AI, probably more widely known as machine learning, really went from a very niche academic field to now, as you all know, one of the most important forces in the entire industry. This change didn't happen overnight. It was a series of pretty massive and distinct paradigm shifts. So today we have me breaking down my understanding of several major milestones over the past 10 years that got us where we are in AI. So, chapter one is, let's call it the chapter of deep learning. This was roughly from 2015 to 2017. So, in the time, every AI project was pretty much an isolated and expensive silo. So, I'll go more into detail about what this means, but remember that the core data structure back then for any AI algorithm is a neural network, or more specifically, a deep neural network. So, a neural network is basically a brain. Think of it as similar to an actual human or animal brain that represents some information. So you have some input, and then you have a collection of neurons or brain cells that encode data, and then a collection of synapses or connections between the brain cells. In mammalian learning science, information and learning is represented as changes in the weights between a neuron. So when one neuron fires, how likely a second neuron will fire. And then you imagine trillions of these neurons connected together in a mesh, and that's a neural network. The same way as mammals learn, artificial intelligence or robots also represent knowledge in these giant neural networks. And using an algorithm called backpropagation, the model updates the weights of these synapses to encode concepts. Imagine a person seeing an image of a cat versus hearing like the sound of a piano. It's going to lead to activation of different representations in this neural network. So let's talk about the field at the time. It was pretty specialist and it was pretty siloed. It was specialist because each task is considered very distinct. Neural networks are very domain specific. A neural network that's aimed to discriminate between images is going to have no overlap with another neural network that's aimed to classify text into positive and negative samples. It is intensive. Companies would need to collect a very large amount of data and operate very long life cycles to train this neural network to learn differences between classes. And because of that, data collection is a very intensive process. Lots of time in the machine learning cycle is spent on collecting data, labeling this data, and then actually feeding it through specialized learning algorithms. Due to this specialist nature, big tech companies get ahead by implementing unique architectures, such as recurrent neural networks or convolutional neural networks. So of these, specifically, there's a class of recurrent neural networks called the long short-term memory network, or LSTM, that really was the backbone of anything to do with natural language. So one of the big moments or technological breakthroughs from chapter one was in 2016, where Google Translate switched from using a statistical learning algorithm to using a LSTM to translate between languages. And the other thing I mentioned about chapter one is that it was very siloed. So all the models, the data, and the code used for these deep learning algorithms were proprietary, and they were locked inside very few concentrated players in big tech, specifically Google, Microsoft, and Facebook. Let's think about a task where we would be using AI at the time. So this task is sentiment analysis, classifying a news article into either a positive or negative sentiment. So back in the time, how would someone do it? How would Facebook do something like that? So you need to collect a very large corpus of product reviews, something at least 100,000 product reviews. You pay people using crowdsourced marketplaces for data labeling, such as Mechanical Turk, to label every single sample. And then you would train this dedicated LSTM model just to output either a positive or negative label. And this model is just doing that. It can't be reused for any other task. You can see that this is a very domain-specific, very isolated and specialized era with tech concentrated among very few selected large companies. Let's talk about some technological breakthroughs or big moments at the time. So we had mentioned Google Translate in 2016 for natural language processing. And in 2015, there was actually a bigger moment, ResNet, or residual networks. This was a paper published by Microsoft Research, which showed that it is possible to achieve better performance by going even deeper. So we mentioned these neural networks that have many layers of neuron connections. And back in the time, there was a bottleneck because the accuracy of a machine learning model would start to deteriorate with the more layers you add. But ResNet in 2015 got around this by introducing skip-level connections between neural network layers so that models could actually become better by going even deeper. So this was a moment in computer vision that allowed deep learning to really scale for any computer vision task. And the third major technological breakthrough really is not in computer vision, it's not in natural language processing, but rather it's in reinforcement learning. So you might have heard of AlphaGo. So this was in 2016 where a company, DeepMind, at the time it had nothing to do with Google, but DeepMind combined this idea of deep learning and using backpropagation to train neural networks with reinforcement learning, which has been a completely separate field at the time. So the key paper behind this was Mastering the Game of Go with Deep Neural Networks and Tree Search. So this is the first time using reinforcement learning and deep learning together, we had an artificial intelligence that could outperform a human in a very difficult task, which is Go. Like when many of us think about the agricultural revolution of AI, then we would think about this moment where finally an AI just trained by a big evil incorporation managed to beat the world's best Go player, Lee Sedol, and very convincingly. So we covered 2015 to 2017. So that was the chapter of deep learning where, we talked about each project as completely isolated, expensive, intensive, and siloed. So next, let's move to chapter 2. This is the time of transfer learning, roughly around 2017 to 2019. We call this transfer learning because it was an era of sharing and generalization, really. So in the past chapter, the tech was concentrated in these few big players. But in chapter 2, we see that smaller companies and startups can start to compete in the field of machine learning by taking these models trained by big companies and then transfer them to their specific domains. You might have a company that's working on sentiment analysis. You have another that's an expert in image classifications for sport or animals, for example. And for the first time, you're now able to take the work from these big companies and then adapt it to your own domain. This is really the first major revolution in democratizing AI. And it really starts with one paper. And this paper, published again by Google in 2017, is the most important paper in AI over the last 10 years. It has a funny name, Attention is All You Need. This breakthrough here is also drawn from the study of cognition in mammals. We discussed the concept of neural networks, and here the concept of attention is what came up. So specifically in AI, we have a term called self-attention. which means sentences or objects are understood in how much they attend to other words in the sentence or other objects in an image. So that sounds a bit abstract, but let me give you one example. So let's look at this sentence. The animal didn't cross the street because it was too tired. When you look at the word it, you know that it is referring to the animal. Words in the sentence are modeled by their relation to other words. And this is the idea of paying more attention to certain things. And it is the same as humans and animals. We attend to different things in the world. We select things to attend to more than other things. And this can be modeled as a matrix of attention weights. These are also context-dependent weights, meaning that for a particular sentence, we can train an AI model to look at different things and pay attention to different things compared to a different sentence. So this was the key innovation, and the result of it is that, remember when we were talking about long short-term memory networks, where tokens are processed sequentially, and one word is fed into a recurrent neural network to refine the representation over time. But now with self-attention, you're able to process an entire sentence in parallel. And that's the key breakthrough. All the words in the sentence are fed in one matrix to the neural network instead of one by one. And that's the beauty of self-attention. In this paper, the authors introduced this transformer, which is basically repeated blocks of self-attention. So when you have a sentence and you teach different words to pay attention to different words, then you have a new representation of how the sentences pay attention to each other, and you take that new vector and you do it again. Like, how do the new combinations of the words pay attention to the new combinations of words? And you stack self-attention layers on top of each other, and you get this new data structure called the transformer. There's actually another main paper that Google also introduced in 2018, which is called BERT, B-E-R-T. There's a whole family of BERT products, Albert, dBERT, Robert, Roberta, and so on. But it all came from this BERT paper, which stands for bidirectional transformers, or bidirectional encoder representations from transformers. Technically, BERT is taking the part of the transformer that is encoding the sentence, so this stack of attention layers, and using it to encode a sentence or give a numerical representation of a sentence. And crucially, you can take this task, the result of this task, and apply it to many other tasks, such as sentiment classification, text classification, translation even, and rating, and ranking, and recommendation. So the most important thing here is that Google didn't just train this transformer model, but it actually open sourced it. It shared the weights with the world. And this is where this idea of sharing starts. We now see an explosion of natural language processing startups that what would take 1,000 lines of research implementation to train a model for sentiment analysis would now take 3 lines of code. There's a new startup called Hugging Face, which is basically a marketplace for models, data sets, and code for machine learning. It is a silo-breaking product because machine learning companies would train their large transformer models, and then subsequent users can take the trained models and fine-tune it. So this is the era of fine-tuning. You take a pre-trained model that has 100,000 labels for sentiment analysis, and then you get 1,000 more labeled examples that specifically contain data you need for your company, and then you just fine-tune it for an afternoon instead of painstakingly training the original data from scratch for days. Just to recap, Chapter 2, or the era of transfer learning, is where smaller companies start to compete in the field of deep learning by taking these larger models that are more generalized now and can be used for many other tasks by simply adding some more data, taking the pre-trained component, which is most of the neural network, based on a transformer, and then fine-tuning it for a specific purpose with companies' proprietary data. But something big is coming. So in 2020, we moved to a completely new era, chapter 3. So this is no longer about fine-tuning or transfer learning. It is the era of application engineering. So I would say this roughly lasted from 2020 to 2023. And this is the shift that brought AI to the masses. So this is where models based on the transformer architecture got so big that we stopped running them and just started calling them. I'm sure everyone here has heard of ChatGPT. And when we talk about the technology, really the big bang paper was GPT-3. So GPT stands for Generative Pre-trained Transformer. And it's actually taking the decoder part of the transformer, where BERT was taking the encoder part of the transformer. So why do we have encoder and decoder parts? The encoder takes an original text sequence and encodes it into numeric representation. The decoder takes the numeric representation from the encoder and then produces a new sequence. This is useful for sequence-to-sequence tasks, for example, translation. And GPT is simply taking some text, encoding it, but then asking the transformer to generate more text. So it's using the decoder, which outputs a new sequence. And I mentioned specifically GPT-3. Of course, there's GPT-1, which was in 2018. We have GPT-2, GPT-3, and then actually we have 3.5 followed by 4. And the big thing with GPT-3 is how big it was. So when you look at GPT-1, it only had 117 synapses, so 117 weights. GPT-3 moved to 175 billion parameters. And it showed that just with a few examples, the transformer model could solve tasks. Like when we mentioned fine-tuning, we still needed thousands of examples, but in GPT-3, you just needed to give the transformer a few examples for it to be able to carry out a new task. So this is GPT-3, I would consider to be the first large language model. So it is quite controversial in the field what is defined as large, but personally, I see GPT-3 as the first large language model with more than 10 billion parameters. And GPT-3 was the model that ushered the new era of pre-train, prompt, and predict. So instead of fine-tuning, now you can get a single model, which is generalized to do any text-related task, and use it to do any task you want. Not even feeding any new data to actually update the weights of the model, but simply taking the model that's already pre-trained and letting it generate more text. For a translation task, you say, translate the following text, and you put in the text. For sentiment classification task, you simply say, is the following news article positive or negative? And then you feed in the news article. I'm attaching a new paper, Pre-train, Prompt, and Predict, here for your reference. It really surveys the shift from like pre-training and prompt and fine-tuning to now simply pre-training and prompting. So when we look at all the GPT models, GPT-3 was the main technological breakthrough for few-shot learning and generalizing to new tasks. As the original name of the article is, language models are few-shot learners, just with a few examples on a new task, like that the model was not originally trained on. A language model can learn to do it with just a few examples. So let's take an example of classifying between two articles that are good or bad. So you feed in the summary of an article and you say, this is positive example. You feed in another positive example and you feed in maybe two more negative examples. and then you just feed in the new article in the prompt and ask the AI to classify it. Now when we look at the GPTs, we'll see actually there's a GPT 3.5 just before GPT-4, which was released in 2022. And this is actually born from a landmark paper, Training Language Models to Follow Instructions with Human Feedback. It's very similar to GPT-3. You can see it also has 175 billion parameters, but it used a new algorithm called RLHF, Reinforcement Learning with Human Feedback, to reduce the toxicity of outputs and make sure it is more aligned with human values. We're reinforcing the model to produce more human-friendly outputs through reinforcement learning, specifically by asking a lot of human raters to compare different versions of sentences that are generated by the GPT, and then fine-tuning the model to predict the better one. This is actually the fine-tuning process that we introduced in Chapter 2. And the result of this Instruct GPT technology is a big bang product, which you all know as ChatGPT. This is a chatbot that people are using every day now to do any task they want. So now let's talk about the industry at the time. The models of GPT-3 and soon GPT-4 were too big for anyone to run. So the big companies that produced them, OpenAI, later Anthropic with their Claude models, and this new company called Cohere, they didn't share the models anymore. So they sold access via an API, or application programming interface. So developers who wanted to use the capabilities of large language models simply had to call this API. And the result of this was a leveling effect. The playing field was completely leveled in a new way. You didn't even need a GPU or any knowledge about machine learning. A web developer can take an API key and now build an entire application with better than human accuracy by simply calling one of these large language models. So how we would do sentiment analysis in this era. You simply open a ChatGPT and you type, classify the sentiment of this review. And then you say, is it positive or negative? And then you're done. There's no data, no training required. For more complicated machine learning tasks, such as math word problem solving, in the old era, these problems were impossible to solve other than in academia. But now you can simply use a chain of thought prompting to solve it, which is simply asking the large language model to solve a problem and show your work step by step. So this is the era of prompt engineering. It was nothing to do with machine learning anymore, and more to do with how you get the right outputs from a large language model, simply with better prompts. There was no data scientist anymore. It was everything about application engineering, building complex software architectures that interfaced with these large language models provided by a few companies. So I would like to introduce another core technology in Chapter 3, which is retrieval augmented generation. So this is a glimpse into Chapter 4. It's the start of what we call context engineering. So in big tech, from Chapter 1, we were talking about Google and Microsoft and Facebook. But Big Tech 2.0 introduced some other companies that did what we call vector databases. So this whole idea of retrieval augmented generation is to enrich the context of large language models by feeding in some proprietary data. But proprietary data is very large. So you can't feed in your whole proprietary wiki into the large language model, which is why we do a search process first. So you take a search term, you use it to query or retrieve text from your database, and then you take the text and you feed it back into the large language model. And all this context that you use to encode your text data is stored in a vector database. Compute numerical representations of the sentences and then store it in a database to be efficiently searched. In addition to these large companies, we were seeing some new incumbents that were open source. So instead of publishing these APIs to interface with large language models, we were seeing companies like Meta and Mistral, which is a French company, that were training their large language models and then releasing them completely open source. So with Meta, they were releasing Llama, and Mistral AI was now releasing open source models starting in 2023 that completely rivaled the performance of large closed models from OpenAI and Anthropic. This created a new leveling, and any player in the industry now has a crucial choice. Do you pay for the absolute best model via the API? Or do you run a model that's 95% as good, that's open source, on your own company hardware for better privacy, control, and lower cost? In the industry, we're now seeing two major new product classes. One is a chatbot. So we all know Perplexity, which actually also incorporates with web search, not just proprietary database search, which is the biggest collection of chatbots from different companies and a proxy to use their services in regions where the original model is blocked. We're also seeing the Copilot pattern, which is basically an RAG system that connects a powerful API model to your own personal data to do editing and document management, knowledge management for you. So in the Copilot space, we're seeing products such as Microsoft 365 Copilot, Notion AI, Ask GoodNotes, Khanmigo, which is Khan Academy's AI, and Duolingo Max, which is an AI companion that simulates certain situations and lets the user interact with it conversationally to improve their language learning. So lastly, let's talk about chapter 4, which is where AI became mostly around multimodal agents. So we introduced context engineering slightly. So that's the concept of getting the data and specific programs into LLMs so that they can perform any task. This is where we are now. So this is the era of multimodal agents. So let's talk about both agents and multimodality. The agent architecture was introduced in the React paper in 2022. So you can also take a look at Andrej Karpathy's introduction of the LLM OS idea. So the whole idea of React is reasoning and action. So the agent takes the reasoning from the LLM to find a specific tool to use and then execute it. So for instance, if a query is take the square root of the current temperature, which is clearly a task everyone would want to do. So you would take a tool that queries the weather. The LLM would decide to do this task via its internal reasoning. It would get the temperature, and then it would go back to the React process and take this number and say we need to now invoke the calculator tool to get the square root. So this is the idea of an agent and external tools. So the planning process, as we introduced, is using the LLM to think about what's the next step to do, or you could go into this React loop, which is take a observation of the world, think about what to do next, perform the action, and then take another observation of the world, which is more iterative process. So in this conception of the LLM operating system, you have the tools, the planning, and then you have short-term memory, which is simply the conversation history of your chatbot, and long-term memory, which contains all the elements of your proprietary data set that you can perform RAG to search and feed in the necessary context into your agent. And tools are used to perform some action. So this is the whole new building block and the key technology of this era, like an actual brain that it's getting more and more similar to the human brain, with elements of memory interacting with the external world via tools and more sophisticated planning using language. And all of this is part of the agent architecture. With agents, we're now seeing products that can browse the web for complex tasks, run and write code. So we all know about vibe coding, which is using products such as Cursor and V0 to write production-ready software. And many great products now, at least in prototype stage, are built without needing to write a single line of code. And then you have agents who do flight booking or travel planning end to end. You simply say your travel dates and your destination, and this whole agent would be able to look at the weather, book the flights, book your hotel, interact with you to get your feedback, and autonomously complete these tasks end to end. This is what LLM agents are about, that you hear about all the time. And then the second key shift from chapter 4 is multimodality. So large language models were no longer simply operating on text. They were taking inputs of any modality, from image to video to audio, and also being able to output all of these modalities, image, video, and audio. When we talk about multimodality, we think about understanding, which is being able to take inputs that are not text, and then being able to generate some text. We have key players such as Google's Gemini, Anthropic Claude that are built to be multimodal. And then OpenAI's GPT-4o, where Omni in the O actually stands for fluidly handling text, audio, and vision. On the generation side of things, multimodal LLMs can actually take a prompt and then generate a video end-to-end. So you see models like OpenAI's Sora and Gemini's Veo 3 able to autonomously generate very lifelike and realistic video clips from just a text prompt. And if we go back to a classic ML task of math word problem solving, you simply take a photo of your kid's handwritten math homework and you say, my daughter is stuck on problem 3. Can you see where she went wrong? And explain the concept to her like a 5th grader. And then the AI would see the screenshot, read it, and then generate the reasoning and output the right thing to the user. So you see how much has changed just in 2 or 3 years. Combining multimodality with agents, patterns, has created vast implication across fields. So in education, you can now imagine AI tutors that can simply watch a student solve a math problem on a whiteboard and then give them real-time verbal feedback. And in the productivity sector, for example, you can picture AI that joins your Zoom call, sees a presentation, listens to the debate, and then automatically drafts the project plan, assigning action items to different participants even before the call ends, and then sending out the whole meeting transcript and some action item notes to all of the participants. That was the whole story about AI over the last 10 years. So I just want to show you this table that recaps everything. In the deep learning era, we started as data scientists, building very specialized models in very expensive silos. Then we became machine learning engineers, fine-tuning models that were shared by a global community led by players such as Hugging Face. Then we became prompt engineers, or the better term is application engineers, prompting powerful large language model APIs and building apps with new ML ops tools such as LangChain and vector databases like Pinecone. And all this tech created Big Tech 2.0, which is originally Big Tech from chapter 1. And then you put on these database companies like Pinecone and Chroma and so on. And then lastly, over the last 2 years, we became, the sexy term is context engineers. So we now feed multi-sensory data to AI partners with a critical choice between now open source models that were possibly a little worse, but gives you more privacy and control, and closed API models that were really at the state of the art. And when we talk about papers, always remember that in the deep learning age, we had the ResNet paper, we had AlphaGo, which really was the major Big Bang moment in AI. And then we had this core breakthrough paper, most important paper over the 10 years, saying attention, the way humans pay attention, can be also taught to AI. And this is everything that you need. And then you have downstream architectures such as BERT and GPT-3 that are based on attention. And then ChatGPT came up using Instruct GPT, which performed reinforcement learning on top of existing large language models. When we talk about the industry patterns that emerged, we think about deep learning in the beginning, and then we move to this era of fine-tuning pre-trained models. And then furthermore, just using prompt engineering and putting on additional context with RAG to create sophisticated chatbots and copilot programs, to now sophisticated LLM agent architectures that can operate autonomously, and you let it run for days and it will solve very complicated problems for you. And when we remember the core technology, we always start with deep neural networks, and then the transformer, which is a deep neural network with this attention. And then we move to large language models when we hit the 10 billion threshold, in my opinion at least. And then to context engineering, where the LLMs became multimodal and could take video, image, and sound data off the shelf, and then possibly even create video, image, and sound outputs. When we look at tasks such as sentiment analysis, classifying articles into positive or negative, we started with painstakingly collecting and training large models and gradually iterating and refining them with hundreds and thousands of data points, to only requiring thousands of data points because you could use pre-trained models that do something more general, to only requiring 3 or 4 examples to put into a prompt. So anyone could do sentiment analysis now with some examples, to now simply taking a screenshot of an article and then asking the LLM if it's positive or negative. And for a second example of math word problems, like this was not possible to solve for any of us except for university labs that were working on computer algebra systems, to being possible to do with some simple prompting techniques. And now to, again, just taking a picture and then being able to get the solution to the problem. So I hope this gives you some foundational knowledge about how AI evolved in the past 10 years. And you can see that it's not just a story about tech, it's a tension between closed proprietary power of some big tech companies and the open community's drive to level the playing field for everyone. And the race is just getting started.